Recording. All right. Hi class, so let's welcome Fouad to give us a second tutorial on like focus on nanofabrication tools. Thanks, Fouad. The floor is yours.
Thank you. I'll share the screen and I'll go to my talk. Okay, so you see my screen, the presentation. Okay,
yes.
So today we are going to talk about a simple approach to reactive and etching, but it is more than that because also I will be talking about etching high aspect ratio structure and application in photonic circuit or integrated photonics. I will be also talking a little bit about gallium nitride. And again, in any subject of these, if you have comments, question, or later, please feel free to contact me. I'm happy to discuss further. So when we talk about plasma, we are talking, sometimes you read it as a plasma etching, reactive ion etching, sometimes even dry etching. So I have to say dry etching is a little bit more wider because, for example, a technique like what we call CAIB, chemically assisted ion beam etching, is also dry etching technique. But reactive ion etching and plasma etching are really common. They have a common the plasma, which means that we are using gases in the fourth state of matter that we call plasma. Of course, here we are not talking about the plasma of the blood. So just a few general things to mention about the plasma. So when you have a gas and you hold it at a certain pressure and you submit some electrical potential on it, it causes the partial ionization of the gas atom. And then collision can be frequent in the plasma. So there is one parameter we call the mean free path, is given by this formula, which is lambda is the mean free path. And that is the average distance that an atom will travel in a plasma before it hurts another ion. And because when it hit another ion, you lose this ion in your plasma. So that is a factor we need to have in mind when you are doing etching. I'll come to that later. But the more efficient plasma will be a plasma at lower pressure, because you see the mean free path is inversely proportional to the pressure in the reaction chamber. So here is, but it's also depending on the gas itself. So that's why for different gases, the mean free path at a certain pressure, here I'm talking always about 10⁻³ torr, which is 1 millitorr. I don't know in which unit you are familiar to use, but note that 1 millitorr is 7.6 Pascal. So I don't know if you are working in Pascal. So now the plasma, typical chamber will be chamber like this. We have the gas feed from top. You have 2 electrodes. The gases are somewhere here. You put a potential against between the electrode. You ionize the gases and you get the plasma. And this is what we call the sheath. The sheath is where you have the ion hitting the electrode. And these ions are important in reactive ion etching because it gives energy. So we will discuss this later in detail. Nowadays, we talk also about high density plasma, and the most common nowadays is the inductively coupled plasma. There are other forms of high density plasma, like expanding thermal plasma or microwave plasma, or even what we call ECR, electron cyclotron resonance plasma. But these are more or less, since the advent of the inductively coupled plasma, it makes the reactor much more simpler and cheaper. So the other technology more or less disappeared. And inductively coupled plasma is now very common in various fabrication labs. So high density plasma, if compared to what I call the parallel plate reactor, you see that we work at lower pressure. The gas flow is more or less in the same range. The power can be higher depending on the configuration of the machine. The frequency of the high density plasma in ICP case, it is 13.56 megahertz, which is the same frequency used in capacitive coupling plasma. So these are also other parameters about the electron temperature, electron density. You see the electron density is higher in high density plasma, and that will give you higher etching rate. But at the same time, we can control much better the ion energy and reduce the damages that we can induce to the structure. So basically what you need when you are doing reactive ion etching, you need to dissociate the molecule of your sample to be etched, because the molecules are in a matrix. So they are bonds, and you need to break this bond to make the atom free, to make a reaction and react with something else. And obviously you want that product, that etching product, to be volatile, so it can be pumped away during the etching process. So other criteria is, of course, the electrode temperature. When I say electrode, it's also the wafer temperature. But also things important are selectivity to mask. So you have to have a good choice of mask and how you pattern it. But we will go along these aspects in later. So basically, when you are doing a plasma etching, and if you have a fluorine gas or chlorine gas or oxygen, you are mainly working with radical. So you have radical, and you have ions. They can be positive or negative, and electrons. But for the etching, you need the radical, in fact, because if you look at CF4, CF4 is an inert gas in itself. It does not react with silicon, even at high temperature. But when you put it in a plasma chamber and you ionize the CF4, you dissociate it in fluorine radical. And the fluorine radical reacts spontaneously with silicon to form tetrafluoride, silicon tetrafluoride, which is very volatile. So that is the most common etching product when you are etching silicon. Reactive ion etching. So that is not from me, it's a very old paper. It shows here the etching rate when you are using xenon bifluoride only in a plasma etching. So the etching rate is quite low. And if you etch with argon ion, the etching rate is also low, sorry. But when you combine argon and xenon bifluoride, the etching rate is not only the sum, it's much more than that. And that's what we call the synergy, that the ion is helping to get more xenon bifluoride ionized and contributing to the etching process. Now, in general, in reactive ion etching, we have three basic chemistry we can talk about. Well, I mean, there is also one more after, I'll talk about it. But for etching silicon or 3,5 semiconductors, chlorine-based chemistry, so that can be chlorine, that can be silicon tetrachloride, BCl3, even HBr, I included in the chlorine-based. So these are all halogen-based gases. Fluorine is also halogen, of course, but fluorine is mainly used in etching silicon oxide, silicon nitride, amorph silicon, or crystalline silicon. And then there's another chemistry called methane hydrogen. That is basically used, it has a slow etching rate, but it's used mainly in 3,5 semiconductor when people don't want to have a corrosive gas like chlorine. And depending, of course, on the application, but it has limitation. So here I want to talk about how you choose your chemistry. So if suppose you want to etch a product AB, that can be anything. We just leave it now as AB, we call it. And so you can consider the three scenarios. If you use a chlorine-based, you will be having a product with A and CLX, B CLX. With a fluorine, it will be AF. And with methane-based, it will be with trimethyl or hydride. So you need to choose the chemistry that it give you a product which has a very low boiling point. Because when it has a very low boiling point, it means that in the experimental condition, it is volatile. When you are etching with reactive and etching, you need to have to etch the product, but you need also to evacuate the etching product. So that's why you need to consider the lowest boiling point. And I'm giving you an example in the next slide. So in the next slide, I'm considering a material that I personally never etched. Zinc oxide is now taking more importance in the semiconductor industry as an ultraviolet light source as well. But when if you want to etch zinc oxide and you want to etch it with chlorine, you see the etching product is zinc bichloride. It has a boiling point of 732 degrees C, and that is the boiling point at 1 atmosphere. Zinc bifluoride is even worse, is much higher boiling temperature. If you use methane, you get a trimethyl zinc, which is a volatile because it's basically used as a zinc source in metal organic vapor phase epitaxy. So then it's evident you use for etching zinc oxide, the best chemistry will be methane hydrogen. Here, that is again the periodic table. I just want to talk about it and was relative to the bond energy. As I mentioned previously, when you are etching a material, you need to break the bond of the molecule in your sample. You know that crystalline silicon, for example, every silicon atom is connected to 4 silicon atoms. But of course, on the surface, depending on the orientation, it has 3 or 2 bonds to silicon. Nevertheless, when you are etching silicon, you need to break these bonds to make the silicon free, to react with the fluorine gas, for example, and form the silicon tetrafluoride, and that will be volatile during the process. So the bond energy, it means that if a material has a high bond energy, then you should expect etching rate will be lower. It won't be very high. And so when you look at this table, you know that the bond between atom is made with the external electron on the outer shell. So when you consider carbon, but of course I want to consider diamond and not carbon as carbon. Diamond has also the same structure as silicon. We saw it in last tutorial. And carbon has only 6 atoms in total and 4 on the outer shell. So the attraction between these electrons and the nucleus of the atom is very strong. And so the bond energy will be much higher. That is, in fact, next slide, I'm talking about diamond. The bond energy of diamond will be much higher than silicon carbide, which is higher than silicon, which is higher than germanium. So if you are etching silicon carbide, for example, or silicon, and with the same under the same condition, you would expect etching rate of diamond is much less than silicon carbide, much less than silicon, much less, also lower than germanium. And the same stand for 3,5. So 3,5, when you consider these atoms, boron nitride, aluminum nitride, gallium nitride, are having higher energy than aluminum phosphide, gallium phosphide, or gallium arsenide, or antimony. So you get the same issue as well, that etching gallium nitride will be lower than etching rate of gallium arsenide. Here we're talking about the same condition in the same chamber under the same condition, of course, this comparison. Another topic I'd like just to touch very briefly. In wet etching, when we talk about isotropy and anisotropy, it's related to crystal orientation. In wet, and that is in wet etching as well. In dry etching, when we talk about isotropic, it means you are etching in all directions more or less at the same rate. So you get this type of shape, you know, circular shape. If you are doing anisotropic etch, you are going vertical with minimum side edge. Of course, 100% anisotropic may be very difficult to achieve. You have always to compromise, and I'll give some example later about anisotropic etch. So another effect you need to think about is the loading effect. So if you are etching, for example, I don't know if you have done all reactive and etching, but most of the time you use a carrier wafer. Let us consider we have a carrier wafer of 4-inch size. And if you are putting a small sample on it of another material like gallium arsenide, and you are using chemistry to etch the gallium arsenide, you have loading effect that you don't have the same etching rate if your size of the sample is varying. If you use very simple small size, you get more ion going to your sample and you get higher etching rate than if you are using a small sample, larger sample. Larger sample, it has larger surface, it consumes more ion. So this effect is very strong, especially with methane hydrogen chemistry. It's less present with the chlorine because, as you know, chlorine etch everything. So you don't have the loading effect when you are etching with the chlorine using, for example, indium phosphide glued on a silicon wafer. But keep it in mind that you may get this kind of variation when you are doing etching. Don't be surprised. Another effect I want to talk about it is the lag effect. So when you are etching structure, if you are etching white structure, you get a certain etching rate. If you are reducing the size of your structure and you are going below sub-micrometer, expect that the narrower your structure is, the lower the etching rate. And here you see that etching rate from 900 nanometer to 100 nanometer in the same run, you see it's very different. And here the decrease is exponential. So if you are working on photonic crystal, bear in mind you need much longer etching rate to achieve the depth you want compared to the etching rate of larger structure. This is indium phosphide etched in chlorine argon hydrogen chemistry. And that is just the same table, you know, the value of the etch rate in micrometer at that depth. Another factor you need to pay attention to it is the micromasking. And I will be touching two types of micromasking here. So this two photographs, they are two samples used at the same time. If you have done etching in ICP, for example, most of the time you can either put your sample as it is on a silicon wafer and etch it, or you can glue it with some what we call heat sink paste here. The heat sink paste allow you to have the same temperature between the sample you are gluing on the silicon wafer and your silicon wafer. So when you are etching indium phosphide, and if you are working at room temperature or here at 60 degrees with this chemistry, you obtain this type of etching with a lot of micromasking, needles form, and that is all indium phosphide, there's nothing else. And And while if you are not using heat sink, you get more or less a smooth and nice etch. As I said, these were etched at the same time. And this one, what is happening is that the temperature of this sample is very low. It is maintained at 60 degrees. And the etching product, indium trichloride, is not volatile at this temperature. And that will cause this micromasking. In this sample, no heat sink, then the temperature of the sample, indium phosphide sample, gets much higher than the substrate, the silicon wafer, carrier wafer. And that will help to avoid getting any micromasking. But more elegant way to get a very good etch is to use heat sink paste, but work at high temperature. So 200 degrees, you see, we get very smooth vertical sidewall of indium phosphide, and these can be used as indium phosphide-based waveguide if you are doing devices. Another micromasking I got during my work with RIE is I put 3 samples. One is N indium phosphide, one is P indium phosphide. Again, I have to. And one is semi-insulating. And after 90 seconds, 1.5 minute etching, you see that the 2 conductive substrates are okay, but this one is ending with a very rough surface. So then I investigated further, and etching 4 minutes, it ended up with the same needle, more or less, we obtained before. Though here we were not using heat sink paste in this case here again. And so you see here the micromasking, and with heat sink paste, you get it very smooth again. So here, etching at 200 degrees, it means that the micromasking is coming from from excessive heating of the sample in this case. So it's completely different micromasking than the first we talk about. And you see even here, when you consume your mask, you get still the same micromasking as in the bottom. And this is due to polymerization. As I said before, we are using methane hydrogen chlorine here. And probably very high temperature, the methane is polymerizing and creating this micromasking that we are seeing here. But still, here it's a remedy how you can remove it. So I finished this part with general aspects. So we talked about lag effect, about loading, about micromasking, and how to choose the chemistry. Now I'm giving to you a few slides about etching dielectric.
And sorry to interrupt you, so I have a question about indium phosphide etching. So preferably, yes. like GaN, I prefer like low temperature etching, like 30 degrees C, right? We want to, or even people find that even lower temperature, that will give you better etching profile. But for indium phosphide, like the higher temperature is better. But there are different opinions. So I see many. So some are etched in 60 degrees C, but some are targeted at 200 degrees C. So like, in your experience, do you have like, what is but like even at 200 degrees C, it's still required to use a thermal paste, so that we still need to like very
Here you use the heat sink paste.
Yeah.
But
so why do we need a heat sink? So if higher temperature is better, why do we still need a heat sink for indium phosphide etching?
Well, I mean, there are 2 aspects here. You want to have a repeatable process. So you don't want to be in a random process where you don't know what is the temperature.
Mm-hmm.
So that's why with the heat sink paste, at least you know what is happening. And if you need higher temperature, you can go to 250. Most ICP system, depending on the manufacturer, depending on the manufacturer. I think the Oxford Plus ICP system can go to 300 degrees.
Yeah.
But other competitor like Plasma Term or Samco, the Japanese company, I don't think you can go so high because the heating of the electrode is done in a different way.
I see.
So, but I will show example where.
I'm just surprised that the operating temperature has a very large range. For example, in GaN normally we're talking about 10 degrees C to 30 degrees C. It's a small range, but for indium phosphide we're talking about 60 degrees C to 200 or even 250 degrees C. So
yeah,
well, this is one thing I'm always confused about. Yeah.
Well, as I mentioned to you here before, where I am now, the etching product indium trichloride is not volatile at temperature. So normally we said indium trichloride is volatile at temperature about 160 degrees at the pressure you are working at in this machine.
Yeah, so in this case, if they are not volatile until 150 degrees C, so why will 60 degrees C still work?
Well, here, because there's no heat sink, so this effective temperature is much higher.
Oh, okay, I got it. Yeah.
So your electrode is at 60 degree. The silicon wafer is 60 degree, but the sample that you just put on top, it may be 200 degree. We don't know.
I see. So like if
we have done some we have done some tests, you know, with these temp.
I see. The 60 degree recipe is actually sacrificing the process repeatability, right? Because it really relies on, okay, got it. Thank you.
So you don't know what is the real temperature, but we did some experiment with, you know, temperature sensitive tape. You put it on the bottom of the sample. With this value of ICP power, we found that in 30 seconds, the sample, even if it is on a 60 degree electrode, it gets to 200 degrees in 30 seconds only during the process.
Wow, that's impressive.
So if you are doing a process very long, like 5 minutes, you don't know what temperature it's ending. And that's why if you want something repeatable, it's better to work with heat sink based and higher temperature. You know what you are getting. And we have done the work we did to use this technology in photonic and integrated circuit, photonic integrated circuit. We use it at 200 degrees, in fact. But I'll show some example at the end. Does it answer your question? Yes.
Yes, I have one question. Maybe it's a silly question, but do you mean put heat sink paste between holder and substrate? Yes.
Yes, that's it. You know, usually you cover the back surface of your sample with this heat sink paste, and you push it on your silicon wafer carrier.
Okay, thank you.
Yeah. So for etching silicon oxide, silicon nitride, basically you need a fluorine chemistry. You can etch it with a chlorine, but it's not efficient. So you are better off to etch it with fluorine like. And basically the reaction are similar. You always get the silicon tetrafluoride as an etching product. I personally use most of the time CHF3 or SF6, but there are plenty of gases with fluorine that they are used commonly in the semiconductor industry. SF6 can offer some selectivity when you are etching silicon nitride. You can etch silicon nitride faster than silicon oxide, I found. But yeah, I didn't really determine in all conditions, but I've did some example and we have seen this. So depending again, that's why in my work on etching silicon indium phosphide, I started with silicon nitride as a mask, but later I switched to silicon oxide. So here is etching silicon oxide in a form of very high aspect ratio and very small, you know. So here we are talking, this is 100 nanometers. So I think this is about 1 micron, I think. And this is even smaller. This is probably 300 or 400 nanometers, I think 400 nanometer. So you see the difference under the same condition. I don't have the full condition, but I can dig it out if somebody is interested. At 400 watt ICP, you see you have a slanted shape, slightly conical. If you go to higher ICP power, you get it more vertical. And sometimes, if you are really interested in high aspect ratio etching, then consider going to higher power of ICP. But again, that is depending on the other parameter of the process as well. Here I'm etching silicon and ICP using a combination of CHF3 and SF6. So you know CHF3 is I was using for etching silicon oxide, but SF6 is more commonly used to etch silicon. But SF6 will give you more isotropic etch, so you get slanted shape. And here I was trying to, with all this chemistry, to try to find an optimum that you etch more or less vertical the material. So you see a small variation of the ratio of CHF3 to SF6 influence a lot your etching as well. Again, this one was quite very nicely vertical, and it was that's 1.5 micron. And we started with 500 nanometer silicon oxide mask, but you see we still have about 280 nanometer silicon oxide. So here the silicon oxide is not removed, and you see that it is showed in the SEM photo as with a different contrast. This etch ended up with slightly, you get like a baseball bat, you know. Sorry, this one I want to go back on it because you see, when you are using lower ICP power, higher pressure comparatively to these ones, you get more side effect. Now here, so that is the one I show here before. I'm enlarging the photo, but this one I'm using more, the ratio of SF6 is much higher and at a slightly different condition. But here I was trying to obtain a cone shape. So when you reach the cone shape, the mask will collapse. So you don't get it. And you see that's about 8 micron if I consider till here. So that will show you, explain to you that here you have here it is anisotropic etch. Here is more or less an isotropic etch. You are getting also side wall etch. I did some etching of diamond, of course. Yes.
I have a question about silicon etching, because we also use this mixture of gases to etch silicon. I don't clearly understand why do we use this mixture. As you told, fluoride gas is used to isotropic etching, and fluoroform we use for anisotropic, or I don't, because I don't clearly understand why do we use
here,
this mixture. Yes.
Well, I mean, the point is, if you use only CHF3, your etch rate will be limited, and you are etching more or less the same at the same speed your mask. So that's why you add a little bit of SF6 in a way that you are not influencing too much the process. And don't forget, CHF3 will end up also forming some polymer on the mask. So the balance of the parameter, the pressure, the ICP power, RF power, all that will be a balance between how much polymer is deposited, and then you remove it during the etch. But if you have a good equilibrium, you can etch deeper without really influencing etching your mask. That's why the combination of these two gases is important. But if you are looking for isotropic, you can skip completely the CHF3, which commonly we call Freon 23. I don't know if this nomination is still used, but these are the Freon type gases, you know.
And which mask did you use for this?
Here I'm using, well, it's a little bit more than just silicon oxide. I had 500 nanometer silicon oxide, but the silicon oxide was, I had on top of it 50 nanometer of chromium. I will go through this technology after. I'll show you more in detail. So we do lift off 50 nanometer chromium in an EBL process. And then we etch in CHF3 the silicon oxide, and then we switch to this combination CHF3, SF6 to etch the silicon.
Thank you.
Okay. So here I had one time a user, he want to etch diamond. As you know, diamond is basically carbon atom, just a small sip. So the carbon atom, how you etch it? At the beginning, I mentioned the three chemistry, but of course you have oxygen as well. And carbon, you can etch it very easily with oxygen because you form CO2, which is volatile even at room temperature. So you don't need any fuss with it. You just etch it. Diamond you can etch with oxygen. You don't need other gases. If you need the special feature, and you may need some other gases, but obviously for etching indium phosphide, diamond, you don't need anything else. And here we have managed to get about 1 micrometer deep etch in gallium in diamond. Now, I want to touch a little bit. I'm not showing, I have a much larger presentation on gallium nitride etching, but I'm not too much into showing all slides. But I just want to show you that I was using this reactive ion etching of gallium nitride using silicon tetrachloride and argon. And at one time I added SF6. And with silicon tetrachloride argon, I was obtaining this type of etching rate at this RF power. That is, by the way, a parallel plate reactor or capacitive coupling reactor. So it's not ICP. And when I added SF6, even 2 or 4 SCCM, I get about 4 times increase in etching rate. So I was getting interested to know why is that happening. This is the etching surface at 20 millitorr, at 40 millitorr. You see quite nice, smooth, but not very vertical, slightly slanted. But you know, gallium nitride is not an easy material to etch. So with this etching rate in this type of reactor, that was quite relatively high. So I looked at the boundary condition. Boundary condition, it means silicon tetrachloride argon, as I started, but also argon tetra SF6, you see the etch rate is very low. So SF6 is not really helping to etch with the argon much. Argon is 9 nanometer a minute. When you do silicon tetrachloride and SF6, you get a large increase. With the argon is a little bit more. So I try to, and that is with varying the flow of SF6. So you see here, you are getting very low at high flow. So I look in the literature and I saw that etching gallium arsenide had the same effect as well. You see the same type of behavior, like increase was adding SF6 and then it decreased again, sorry. In silicon, the etch rate keep increasing. Let me see here, it's etch rate 4 angstrom. This way here is CL2, very small toward SF6. So you see that is the etching rate variation of polysilicon or oxide. Bottom of the story here, etching gallium nitride. So you see it's working with gallium nitride, it's working with gallium arsenide, but getting this Gaussian shape. In silicon, you continue increasing the etching rate. So I looked at a factor, what we call the boiling point of the product, and you see that the NF3, in case of gallium nitride, has a very low boiling point compared to nitride trichloride. And that's bring me to the conclusion in this story that when you are etching gallium nitride and you use a little bit of fluor with the chlorine, the nitrogen of the gallium nitride is evacuated more as NF3, while the gallium is still evacuated as gallium trichloride. But when you increase too much the fluorine rate, the SF6 rate in the gases, you start forming gallium trifluoride, which is not volatile. And that's why it will decrease the etching rate at higher SF6 flow. And yeah, that is another comparison that you can also consider. When you are using a gas, look at the dissociation enthalpy. That is the energy you need to remove, for example, one chlorine radical from the silicon tetrachloride or one chlorine from BCl3. The same for SF6 and silicon tetrafluoride. And that will explain why other people who use the same combination, like this author here, he didn't find any increase of etching rate of gallium nitride when he used silicon tetrachloride and when he added silicon tetrafluoride. But another person who was using BCl3 and SF6, he managed to get increase of etching rate. And he reported 210 nanometer maximum etch rate at 300 watt. I found at 300 watt, 400 nanometer etching rate with this combination. Again, you see silicon tetrachloride and BCl3, you need less energy to dissociate silicon tetrachloride. So with the same energy, you get more ionization and then higher etching rate. So these are factors you should consider whenever you are using gases to do reactive ion etching. And for instance, chlorine is even better than silicon tetrachloride because pure chlorine gas has a dissociation energy about 60 to 70 kilocal per mole. So it's much easier to dissociate than even silicon tetrachloride. That is my last slide about gallium nitride. We did also some etching of bulk gallium nitride in collaboration with people in Poland. And that is the etching of the gallium polar, and that is the etching of the nitrogen polar in the same chemistry. So the nitrogen polar has higher etching rate, but you get these defect, while in gallium polar, you get very smooth surface. These ray here are from the polishing process beforehand. So it's not induced by the reactive etching. It was induced by the mechanical polishing. And what we were trying here to achieve with this polish group is to remove the damage from the mechanical polishing, that they can grow on it structure. And with this way, they have shown laser work in gallium nitride grown on such structure. The disadvantage of this bulk gallium nitride that the pieces are very small. They can be like half square centimeter only. I don't know now whether this technology has been upscaled. I don't, but that is work done like late 90s, early 2000. When you are etching aluminum containing semiconductor, adding SF6 doesn't help because aluminum trifluoride is very non-volatile. And basically when you are doing a process, you immediately get aluminum trifluoride. And that's why when you add SF6, you can use it to do selective reactive ion etching. For example, if you want to etch gallium arsenide and stop at aluminum gallium arsenide, you can add SF6. And the process, you have better control of stopping at the right time. Just one issue with this technology about gallium nitride, I tried it on ICP and it doesn't work at all. So it only works in capacitive coupling reactor. Okay, keep it in mind. And ICP, even introducing one SCCM of fluorine did decrease the etching rate. It didn't help at all. Any questions so far? Okay, I keep going. Etching indium phosphide with methane hydrogen. I was in a group where we were doing a lot of photonic circuit in indium phosphide based material. And the main technology to etch the waveguide was methane hydrogen. So basically, when you use methane hydrogen, you need to alternate with oxygen plasma to remove what I said, the polymer deposition caused by the methane. So here we did the 30-minute process without any oxygen, and you see that you get a polymer hanging and disturbing your etch. Here we were alternating like 10-second oxygen, 2-minute methane hydrogen, and you can have a good control of the etching process. So bear in mind, depending what chemistry you are using. I did some etching in ICP of with chlorine of indium phosphide. And as I said, we had to go at higher temperature at pressure about 4 millitorr. But to start ICP reactor, I mean, these are standard, I'll just pass it. So I did also some etch of waveguide in indium phosphide using chlorine methane hydrogen process. And you see that we managed to get very low losses of waveguide. So in the about 2 decibel, 1 to 2 decibel per centimeter. Of course, these values are much higher than if you are working, in silicon on insulator. But that is like we were trying to develop a new technology. Then, in fact, not long after, I switched to chlorine argon hydrogen. And here I was playing with the hydrogen flow. So at very low hydrogen process, I maybe need to switch it there. At 3 SCCM hydrogen in this process here, you get a bit of isotropic etch. So the mask has been completely removed and you obtain like pyramidal shape or cone. If you increase the hydrogen, you increase the passivation of the sidewall. So you see here, we have some roughness. Here we have some roughness on the top. And I need to remove this one here again. I don't know how I get it vertical now. I don't know. I leave it there. Maybe I just, I do it this way. You still see me? Yeah?
Yes, I can still see.
Yeah, okay, because I just wanted to remove that thing. It's a little bit annoying. So here, on these things, here we were using 12 SCCM hydrogen, but you see there is still some erosion here, and that was due to the erosion of the mask itself, in fact. So here we were using 400 nanometer on all this experiment of silicon nitride as a mask. And then we switched to 600 nanometer silicon nitride, and you see this is the same process, and you don't have this effect as you have it here. So you see, you have always to adapt your technology depending on the etch depth you want. And in fact, this investigation was meant to try to get DBR type grating etch on chip. So for deep etching requirement, you have, if you want to do optical lithography, think about the mask thickness that you need to have your etching. And as you have seen in previous slide, 600 nanometer of silicon nitride worked much better, and we could open it using the photoresist. In EBL, I tend to go to the technology of lift-off. So we used ZEP to etch 400 nanometer of silicon nitride, but this ZEP layer wasn't enough to etch 600. So for thicker mask, and later I switched to silicon oxide, we needed another technique, as I mentioned. And that is what I call 3-level masking. So you see use of an additional mask, metal mask. So we used ZEP, resist, or PMMA, double layer, to do chromium lift off. And then you etch the silicon oxide, and then you etch the 3,5. And when you finish and you get the structure you want, you remove the silicon oxide and buffer HF. Buffer HF doesn't attack at all the 3,5. So you have a clean process, you remove your mask easily. And if there's still chromium on top, it will go away with the silicon oxide. So we were interested to get deep etching of gratings to have an internal mirror on chip. As I mentioned to you last time, when you are, when you are doing gallium arsenide, no, sorry, I didn't mention it, but gallium arsenide laser, for example, we use the mirror, they are the cleaved facet of the chip. But in indium phosphide, if you want to have an integrated circuit and you need a mirror to have a laser, then you need to have DBR grating to play the role of the mirror. So here we try to develop this technology. And these were the structure we were using for the indium phosphide waveguide. And in this case, we have part which has an active layer to work as a laser. And that was at 1.55 micrometer. So we did investigate first order DBR and third order DBR. Third order DBR, it has a larger gap, so it is easier to achieve in deep etching. So here, this is a photo of a first order DBR grating. And we did manage to get quite deep etching and quite vertical. But third order was a bit easier. Especially you see here that in the middle of the waveguide, you still have a small part of the material remaining. These were the parameter of the ICP etching if people are interested. Again, I was using heatsink paste and 200 degree. And that is a picture, you know, from the etched area where the device would be at the end. And you see, this is not a real laser structure at the moment, but it was simulating low reflective mirror and highly reflective mirror. You know, DBR grating, the more period you have, the higher reflectivity you get. So that was the type of the device we wanted to do. This area will be the SOA, semiconductor optical amplifier or laser, in fact. And the DBR will be deep etching, and the laser area will be shallow etching. So it was a combination of two technology. The small waveguide here was etched with methane hydrogen, and the grating were etched with chlorine. And we managed to get this in a real chip. And you see here, that is after embedding the whole structure with BCB. And this dip here this is the area where we were etching the grating. And after filling with BCB, you get it, you see it this way. And these are the released waveguide. And you know, here we will be putting the contact to activate the laser part. And with this technology, we managed to do multi-wavelength lasers. So in reality, I mean, the aim was at the end 8 wavelengths, but this device here was 4 wavelengths. So with this technology, we managed to get 4 discrete wavelengths matching the ITU grid of the telecommunication. And you see that is the central wavelengths when you don't have. So here, if you are just activating the main laser, you get this wavelength. And then when you activate one of these, you can switch from this one to this one to this one to this one. And these difference were 3.2 nanometer, which is matching, as I mentioned, the ITU grid of the telecommunication. That is a picture I didn't include in my slide, but if you like it, I can send it. But I mean, We were trying also to apply this technology to photonic crystal pillar. And that was a nice picture. My student won an EBL prize from the company RIE in Germany. They do every year a competition of photography, and he sent this photograph with plenty of etched photonic crystal, and he won the first prize that year. Now we use this technology to help another student to do photonic crystal pillar. And so you see here, we have very deep etching, about 6.5 micrometer. Of course, with the pillar, you don't get the same shape, but still, if your device is at this level, you have enough contrast to get it working. And this was the waveguide on the edge. You see quite smooth. And the student who was doing this work, she managed to fabricate a short polarization filter using this pillar. So to eliminate, for example, the transfer, the TM or side of the light. And that was done. That is, of course, we have cleaved here through it to show the device. Another things, I was using the same technique. We try to use it to do photonic crystal. So in the time we were not using still the 400 nanometer silicon mask and opening with ZEP, we managed to get about aspect ratio. You know, aspect ratio is the depth toward the diameter. And we obtain about aspect ratio 10 with 250 nanometer holes and about 3 micron deep etch. But it is, we call it carrot shape. You know, when you are planting a carrot, you get at the end like a point, you know. The same technology, when I use the 3-level masking, we managed to get deeper, about aspect ratio about 80. But unfortunately, the people who were doing the research work on devices have finished their work, so nobody has used this technology on real devices. But it works very well, you see, and the surface on the top is very smooth, contrary to this one where there's more roughness. So that brings me to the end. So in conclusion, briefly, I show you some general rule and effect about reactive ion etching, about the role of chemistry, lag effect, micromasking, loading effect, simple thermodynamic approach, looking at dissociation enthalpy and boiling point of etching product, and then deep etching of indium phosphide and use for photonic application. And basically, this paper is having much of this presentation. That was more like a tutorial paper I published in 2014. And how I go back there? No. Well, okay, okay, here I'm back.
Yeah, thank you so much for it.
Any question?
Any questions from students?
And as I mentioned to you, I think, I mean, at any time, if you have some issue with technology, I don't promise that I'll be able to do everything, but I'm happy to look at the issues and maybe I'll be able to advise.
Yeah, definitely. Like, because our group is we are dealing with all the 3-5 materials, so we are going to do a lot of GaN arsenide and indium phosphide etching. So definitely, your expertise and experience are very, very useful. So yeah,
that's good. Yeah. I'll be more than happy to help. That's not a problem.
Thank you so much. And with that, let's thank Professor Fouad for giving us this wonderful tutorial on especially the 3-5 based etching and for photonic applications. Thank you so much for it.
Thank you. Thank you for your attention.
Thank you.
Thank you. Thank you.
Yeah.
Thank you. Bye.